at triangle congruence. And, you know, one of the things I always wondered as a kid was why we spent so much time talking about triangles. And it never really occurred to me until I got older that triangles make up so many other shapes. So if we know about triangles, we know about like squares, or we can know about pentagons, or hexagons, etc. So all the other shapes are made up of triangles, which I think is, a good reason to know about a triangle. Because again, if we know about this shape, we can apply it to this shape or this shape or this shape. I always get kids say, well, what about a circle? So just real quickly, I do want to show you there's something known as the unit circle. I don't want to go too much into this. You're going to learn the unit circle. Maybe I'll say with triangles. I don't know. I'm not getting the pictures that I want. So you can see that triangles are actually parts of a circle as well, which may not be something that you would think about, but they are, which is kind of interesting. You're going to learn about that your junior year. But again, just trying to say that they really are in all other shapes, including a circle, which is kind of interesting. So that in a nutshell is why we spend so much time on triangles and why it's such an important shape. So at that, we'll jump into it. What does congruence mean, and sort of how do we tell if a triangle is congruent, some shortcuts, etc. for telling that. So it says in chapter 3, you created images using the rigid transformations of reflection, a translation, and a rotation. Today, you will learn how to use rigid transformations to determine whether two polygons are congruent. Read the math notes box about similar polygons in this lesson. The polygons below are similar. The polygons on the left was reduced to create the polygon at the right. What is the scale factor? Find the missing length. So the idea between similar just means that they're the same shape, but not the same size. So if you think of like a Camaro, an actual Camaro car, and a model, they have the same shapes, but they're clearly not the same size. But they have a scale factor where if you took that model and made it a certain times bigger, then it would actually look like, and be the same size as the other car. So what we're looking at is the scale factor here. And one of the things we'd have to do is match this thing up so that it matched up evenly. So I think what we need to do is match up the sides here. So it looks like the 35 and the 14 will match up. It looks like the 25 and the 10 will match up. So the 25 and the y will match up. Well, that must mean that this equals, it doesn't equal 10. It doesn't equal 25. It must equal 10. Right, because the 10 and the 10 are the same as the 25 and the 25. So the z and the 8 are going to match up, and the 17.5 and the x are going to match up. But the question is, what is the scale factor? What do I multiply this 25 by to get it to turn into 10? And what do I multiply this 35 by to get it to turn into 14? So I'll just call scale factor x, and I'll just do a really quick equation. I'll say 35 times x equals 14. I will go over here and solve, and I get 0.4. So it looks like if I multiply by 0.4, I'll get those numbers. So let's check that scale factor here on the calculator. If I multiply 35 by 0.4, I expect to get 14. I keep doing that. 35 times 0.4. I don't get the decimal in there. So I get 14. So if I multiply 25 by 0.4, I expect to get 10. So that's how we know that that's going to be 10. So what if I multiply 17.5 by 0.4? I'll get x. So 17.5 times 0.4 will give me my x, and that equals 7. Well, the question is, how do I go the other way? Because now I know that z times 0.4 is going to end up equaling 8. Well, what I can do is divide by 0.4, and that will tell me what z is. So I'm going to go to the calculator. I'm going to divide 8 by 0.4, and that will give me what z equals, which equals 20. And that should make sense because if I multiply 20 by 0.4, I should get 8. And I do. So I feel pretty confident. I've solved for x, y, and z, and I've also got the scale factor. Remember, the scale factor was 0.4. And I calculated that by using a little bit of algebra. So one thing I want to point out is we know the scale factor is 0.4 in this direction. And we're given that it's this direction. But what if there was no arrow at all? Now what would the scale factor be? Well, most people feel comfortable actually doing the scale factor from smallest to biggest. So maybe we would say something like, all right, well, 14. And again, this is just sort of an addition to this. This isn't part of it. I just want you to see the scale factor could be two things. Going from small to big, it was 0.4. But what is it going from, from big to small, it was 0.4. But what is it going from small to big? Well, I would say 14 times, we'll say this is Q. This will be the scale factor. So 14 times Q equals 35. So if I divide by 14, I get Q equaling 2.5. So in this direction, if I multiply the smaller numbers by 2.5, I get the bigger numbers. If I take the bigger numbers, I multiply by 0.4, I get the smaller numbers. And that makes sense based on things that we've learned in the past here, that if you multiply by a number smaller than one, they get smaller, but if you multiply by a number bigger than one, they get larger. So I just wanted to talk about the fact that the scale factor could go either way. However, we were given the arrow, so this would be the scale factor, not this one, since the arrow was given to us. All right, so now examine the diagram at right. The smaller triangle inside the larger triangle is similar, which is important because we know that they have the same shape, different sizes, but we can calculate the scale factor and that will make it easier for us to solve. So it says write a proportion to solve for x. Well, first of all, I think that the idea, I guess that's fine. So the smaller side would be x. And we know that the proportion is x is the same as x plus 27, right? So that's the relationship. X is the same as x plus 27 in the same way that 11.2 is compared to 28. So this is going to be our proportion. The small side of x is compared to the large side of x plus 27 in the same way that the small side of 11.2 is compared to the large side of 28. Now I can cross multiply and solve, so I get 28x equals 11.2x plus, well, probably be easier to hop over to a calculator here and multiply. I think my calculator's a little bit big these days. See if I can make this smaller. All right, so I'm going to get 11.2 times 27. Which gives me 302.4. Now I can solve. I'll subtract 11.2x from each side. And I will get, what, 16.8x? I'll double check the math on that. Equals 302.4. Then I'll divide by 16.8 if it is indeed 16.8. So let's double check all this math real quickly. The first thing was 28 minus 11.2. And it was 16.8. Now I will divide 302.4 by 16.8. And I'm going to get an x of 18. So x equals 18. And let's see if that makes sense here. I'm going to kind of erase some of this work here. That means that my ratio should be as follows. 18 over 18 plus 27 is 45 should equal 11.2 over 28. So if I cross multiply, they should be equal. So 18 times 28 should be equal to 45 times 11.2. And you can see they are equal. So I feel good about that x equals 8. Now it says determine M and P. Note that when no units are given on measurement, you may assume that the units are the same. Oh, okay, so like feet or inches or whatever. It's not like they're going to go from inches to feet. All right, so now we can go ahead and set up some more equations. Again, this is 18 for the small side, and the large side was 45. I prefer that to the decimal, so we'll say, all right, M compares to M plus P in the same way that 18 compares to 45. So we'll cross multiply. I have two variables here, so I'm not super comfortable with what's happening. 18M plus 18P is going to equal to 45M. I'll subtract 18M. I'm going to get 18P is equal to 27M. So if I divide by 27, M is going to be equals to 2P over 3. So now I have them in the same variable. Instead of using M, I can use it as 2P over 3. I'm not really... Oh, I know what we could have done that would have made way more sense than what I'm doing. I was going to say, like, this book is going crazy with this. What we have here is we have a right triangle, and I think it makes more sense to kind of exploit that right triangle and use that. So let's solve for M by saying that we have the Pythagorean theorem. We have 18 here, 11.2 here, and M here. And then we'll solve for P by saying, actually we'll come back to P in a minute. Let's solve for M first. So we're going to say 18 squared plus 11.2 squared is equal to M squared. Again, just using that right triangle there. So grab my calculator, 18 squared, and I will add that to 11.2 squared. And then I'll take the square root of that. So you see, I just say square root of answer. And I get 21.2. So M equals 21.2. And now, if we look at the big triangle, we have 45 for the big side, 18 plus 27, 28 for this side, and we know that this side is M plus P. Well, we already know what M is, so let's go ahead and figure out what the whole thing is. So we'll say 45 squared plus 28 squared is going to be equal to M plus P squared. So let's do the math on that. 45 squared plus 28 squared equals this. We'll take the square root of that. Square root of the answer. So that'll give us 2809 equals 53. So this whole thing is 53 right here, right? M plus P equals 53. But I already know that M is 21.2. So if I subtract that, 53 minus 21.2, it will give me what P equals. So P equals 31.8. Crazy problem. There's a lot going on here. I'm not sure there's a better way to do this than the way I did it. If there is, I apologize. We know that those add up together to 53. I think I'm right, but I'm just going to pause the video real quick, check the answers, and make sure that I didn't screw something up. Okay, so definitely a rigorous problem. Those answers are correct. M is 21.2, P is 31.8, and X was 18. So a lot going on here, though. All right, so two polygons are congruent if one is the image of the other following a sequence of rigid transformations, reflections, rotations, or translations. That is, there is a sequence of rigid transformations that maps one polygon onto the other. So at this point, you'd be getting our resource page and ask if any of these shapes match up. I gotta be honest, I don't love 7.2 and I don't love 7.3. But the bottom line is that I had written down the answers of what goes together. So E and H, they go together, and you could see if I reflected E, it would turn into H. Another one that goes together is, where did I have all these things written down? Another disappearing on me. Oh, there we go. Okay, so G and L. G and L go together, which I don't know how easy that would be to see, but if we rotated that down and then translated it over, it would line up. And then finally, F and K go together. And again, not super easy to tell. It looks like I would probably have to reflect it and then rotate it and then translate it over. So kind of a pain. Again, F and K go together. L and G go together, and E and H go together. So not my favorite problem. At that point, we will go to the other (711) and finish this thing off. So 7.4 says in problem 7.3, you concluded that if two polygons are congruent, then the corresponding angle measures are equal and the corresponding side lengths are correct. That means, are equal, so congruent means that they're the same shape and the same size. Conversely, if two polygons have equal corresponding angle measures and equal corresponding side lengths, then the two polygons are congruent. And there is a sequence of rigid transformations that maps what's on the other. So it asks us to sketch these two triangles and ask, are they congruent? Well, if they're congruent, they have to have all the same shapes, all the same side lengths, and all the same angles. So one way I can do the side lengths is confirm that 16 squared plus 63 squared would have to equal 65 squared, right? 16, 63, that would make this hypotenuse 65, 16, this would have to be 63. So we'll go ahead and we will say, all right, well, 16 squared plus 63 squared equals 4225. So 65 squared better equal that as well. And if it does, which it does, then we know that this must be 65 and we know that this must be 63, right? The Pythagorean theorem tells us that. The other thing is the triangle angle sum theorem. The triangle angle sum theorem says that all triangles have to add up to 180 degrees. Well, we know these are both 90, right? So the question is, if this is 90 and this is 14.25, what is this angle right here? We'll call this x. If this, we'll see what this adds up to if it equals what x equals to make this equal 180, because if it equals 75.75, well then we can assume that this is 14.25 and then we'll be good on that as well. So we're going to say 180 minus 90 minus 14.25. See, I did not get my decimal. And I get 75.75. So this one must be 75.75. Well, now I can go over here and say the same thing. Hey, this is 90, and hey, this is 70.75, so 75.75. So this must be 14.25. So there we go. All the angles are the same. All the sides are the same. So yes, these triangles are congruent. There should be rigid transformations. So what I could do is rotate this thing down, and then I could translate it up and over so that it matched up perfectly, that they were on top of each other. Now I will say this, to me this triangle looks bigger than this triangle, but that doesn't matter. In this book we have to go by what the numbers say, not what it looks like. So if they don't look congruent, it doesn't matter. If they do look congruent, it doesn't matter. You have to be able to prove it mathematically. So to represent the fact that two polygons are congruent, use the congruent symbol. So you can see it's an equal sign with kind of a little tilde above it. That's the congruent sign. That means same shape and same size. For example, if there's a sequence of rigid transformations that maps triangle ABC onto triangle DEF, then you know they are congruent, and this can be stated as triangle ABC is congruent to triangle DEF. Now there's a couple of things in here that are really important to catch. The order of the letters in the name of each triangle identifies which sides and angles correspond. For example, the congruent statement triangle ABC triangle is congruent to DEF indicates that A and D are the same. And that side BC is the same as side EF. So you would say side AC is the same as side DF, because the order is very important, that the way that they put those in. That's known as a triangle congruent statement. So for example, Luis wanted to write a statement to convey that the two triangles below are congruent. He started with triangle MNP is congruent to, but he got stuck. So they're not oriented the same way. Complete Lewis's statement and describe how you determine the answers. So triangle MNP is congruent to triangle. Well, what we're going to look at is the angles on the sides go together. So M is across from 16. So I'm going to go to 16 and pick the angle that is across from it, and that goes in the same slot. So M and U go together because M is across from 16 and U is across from 16. N is across from 8. So I need the angle that's across from 8. And you can see it's W. And finally, P is across from 20, so I'll go to 20, and you can see V is across. So I know that this is the correct triangle congruent statement if you started as MNP. I will say as well, though, if he had started it as triangle PMN, right? If he had said PMN, that's no problem. We could have gone over here and said, well, I know that P goes with V. I've already determined that, right? P is across from 20 and V is across from 20. And I know that M goes with U. We've already determined that. M is across from 16 and U is across from 16. And I know that N goes with W. And again, we'd already determined that 8 is 8. N is across from 8 and W is across from 8. So there's 6 different ways that you can make a triangle congruent statement correct. This is just 2 of them. But again, you'll always notice that the M and the U match up. They're in the same slot. You always notice that the N and the W match up. They're in the same slot. And the P and the V have to match up as well. They have to be in the same slot as well. So it doesn't matter the order that you choose, but it has to. The second one is important. Now, what sequence of rigid transformations would map the triangle onto the left, onto the one on the right? Well, it looks like I would have to reflect it so that the P moved over here, and then I could translate it down so that it would slide over. So reflecting and then translating it and moving it. So label the triangles and then write a congruent statement for the triangles you sketched in 7.4. So let's go back to 7.4 and so I will name this E, F, G, and H, I, J. And again, it doesn't matter how I start my triangle congruent statement. It matters how I finish it. So I'll say G, E, F, just to be a pest. G is across from 63. So which one's across from 63? The J is. By the way, you'll notice you say triangle, and then you name it, and then you give the congruence, and you say triangle, and you name it. Okay, so now E was across from 65. So I'm going to go with H because that's across from 65. And then F was across from 16, so I'm going to take I as across. So that is a possible triangle congruent statement for these triangles that I just named.